open up my previous version thereof. And just so we can see these things side by side, I'm going to drag that tab over to the right of VS Code and let go. And now you can see the C version still on the left and the Python version at the right. What I'm going to do here now in my Python version is change it to be quite like the version in C now at left. So as promised, I'm going to do from CS50 import get string. Then below that, I'm going to say simply answer equals get string, quote unquote, what's your name, question mark space, no semicolon. But then on the next line, parenthesis. Then on the next line, I'm going to do print, quote unquote, hello, comma, space, step. I'm just going to as well. Which one is better? Like less rigid of the program. There are crucial differences. On Python of hello.py, david, what are we about to see? Hello, comma, what where I wanted it. All right, turns out we can take off one of these training wheels already. I put training wheel off. Why don't we need the main function anymore? Because out that humans in recent years, we don't have to put everything in a class. Public static void main, for those familiar, you can just write system.out.println and get some work done. Yeah? Good question. Is input only for a string? Yes. Right now, it will get input from the user via their keyboard, and you'll get back a string, just like getString. And we'll come back to why that's maybe not a good thing. All right, so what's more might we want to do at this point? Well, let's tease apart some differences now with C. So up until now, every argument we've ever passed into a function in C, and Scratch for that matter, is a so-called positional parameter. And a parameter is the same thing as an argument, but generally when you're looking at the function, from the function's perspective, it's a parameter that it accepts. But when you're calling the function and passing in an input, you call it typically an argument. But they refer to essentially the same thing. And all of the parameters we've been passing into functions thus far have been positional in the sense that the order matters. The first thing, then the second thing, then the third thing, and so forth. For instance, with printf, the first thing has to be the quoted string, maybe with a placeholder. And then if there's another argument after the comma, that can be the second argument, the third argument, and so forth. But it turns out Python additionally supports what are called named parameters, whereby you don't have to rely only on the order in which you're enumerating the arguments to a function. And that's helpful because some functions, especially in the real world, when you start using other people's libraries that have lots of functionality, they might not take just 1 or 2 arguments. They might take 4 arguments, 10 arguments, maybe even more. And it can just be unwieldy to have to remember the precise order of all those arguments. You're just asking for trouble. If you're going to screw up, or a colleague is going to get the order out of whack. So with name parameters, you can actually be explicit with Python and tell it what argument you are trying to pass in by giving it an actual name. So let me go over to VS Code here and propose that we use this for really the simplest of programs in order to override that default new line that we seem to be getting for free just by calling print. In other words, let me go ahead here and clear my terminal window. Let me close hello.c and focus only on hello.py for just a moment. And let's make it much simpler like the very first version and just print out using Python's print function, not printf, quote unquote, hello world, close quote. And now here, I'm going to do Python of hello.py, enter, and we see that the cursor moves to the next line, the $ moves to the next line, because I'm automatically getting a new line. Well, what if you don't want that? How can you override that behavior? Well, you can actually use a named parameter in Python. And I can go up here and add a second argument that if it were just something like this, that would literally print out the word this, because it's just another string. But if I give it a name, like end equals quote unquote, I can override the default behavior of the Python print function by changing the value of its end parameter to be the so-called empty string, quote unquote, which means literally there's nothing there. Watch what happens now. If I run Python of hello.py and hit enter, the $ is weirdly, and sort of in an ugly way, on the same line, just like it was when I made the mistake in C in week 1 of omitting the \n. That is to say, what the default value of this end parameter really is quote unquote \n. And I can make it explicit by changing my code as such. I'm going to go ahead and rerun Python of hello.py, and now the cursor's back on the next line. And not that this is that useful other than overriding that default, but you could do fun things like exclamation point, exclamation point, exclamation point if you really want print to be excited to print some things for you. And if I now run Python of hello.py a third time, now you see that it's ending with exclamation point, exclamation point, exclamation point. Looks a little stupid with the $, so you could even toss in a new line there, run it yet again, and now we sort of get both of those there. But I would say the common case is to use that end named parameter simply to override it. So how do you learn more about these kinds of things? Well, if you go to the official documentation for Python, which is a thing more so than with C. Like if you want to learn more about Python and the functions it offers and the arguments it takes, you go to the official documentation, docs.python.org. This is essentially analogous to the so-called manual pages or man pages that CS50 has a version of, but there is no one de facto source for those man pages. Several different versions of them exist in the wild, whereas Python itself as a community maintains its own official documentation. So for instance, if you go to a specific URL like this, ending in functions.html, you'll see an exhaustive list of all of the functions that come with Python besides just the print function, and we'll see a bunch of more today. If specifically you scroll down to the print documentation, you'll see something that's a little arcane that looks like this. But this is representative of a Python prototype, if you will, often also called a signature, that just tells you the name of a function and then how many and what type of arguments it takes. So how to read this? Well, the print function takes some number of objects. So in Python specifically, this syntax of star objects just means 0 or more objects, whatever that is, like a number or a string or something else, the stuff you want to print out. After that, if you start using named parameters, you can specify what the default separator is, the separator between arguments to print. So recall that when I did quote unquote hello, comma, quote unquote, or quote unquote hello, comma, answer, it was separated automatically for us by a single space, even without my hitting the spacebar inside of my quotes. That's because the default value here is in fact a single space. The default value for end, as promised, is indeed \n, and then there's some other stuff related to file I/O that print can also deal with, but more on that perhaps another time. There's one curiosity here. In Python, it turns out that you can use double quotes or single quotes around strings, where in C it was much more regimented. Double quotes are for strings, and single quotes are for chars, characters only, single characters, it doesn't matter in Python which one you use so long as you're consistent. And stylistically, you should really pick one and go with it. And the only time you should really alternate between the two is maybe if you want to put like an apostrophe for some human's name inside of double quote, inside of single quotes or something like that. But generally, you have a little more flexibility in Python. And you'll see in different languages, Python community tends to use single quotes, at least in the documentation. The JavaScript world tends to use single quotes. We in CS50 often use double quotes just for consistency with what we do in C. But any community or company would typically have its own style guide that dictates which one you should use, if only for consistency. Questions? Then on this here print function as just representative of all of the ducks that you'll see. All right, well, let's take a quick look at variables. We've used these a few times already, but let's focus in a little more detail on what's actually different. In Scratch, if you wanted to create a variable called counter and set it equal to 0, you would use this orange puzzle piece here. In C, you would do something like this: the type of the variable, the name of the variable, and then set it equal to the initial value semicolon. In Python, it's going to be a little similar, but you can probably guess where we're going with this. How is this line of code probably about to change? Yeah. Good, we're not going to bother with int or the data type more generally. We're just going to say counter, because obviously like a smart interpreter can just figure it out from context that you're putting a 0 in there. It's obviously an integer. And what else is about to go away? The semicolon. So this is the C version, and voila, this now is the Python version. And this, as silly as this example is, it's kind of representative of how languages like Python just tend to be a little more programmer friendly, because you just type less and get the same work done. All right, so if we wanted to do something now in Scratch like increment the counter by 1, you would use this puzzle piece here. In C, we could do something like this. In Python, it's going to be almost exactly the same, except of course no semicolon. In C, we could alternatively do this, and you can also do this in Python. In C, though, you could also do what other technique? ++, I'm sorry, but Python has taken that away from us. So if you've gotten to the habit of using ++ or --, that's great. Use them in C all you want. In Python, they just don't exist. So you'll see this more commonly instead as the heuristic. All right, what about the various types that exist in Python? Because even though you don't have to specify the types when declaring your variables, they do in fact actually exist underneath the hood. And it's worth knowing a little something about them, because not knowing will lead often to some form of bug. So in C, we had types like this: bool, char, double, float, int, long, and string, the last of which was thanks to the CS50 library. But last week, we would have started calling a string char star instead, which it still is a data type, the address of some char. In Python, we're going to whittle this list down to a subset of those essentially, whereby we still have bools, we still have floats, we still have ints, and we do have strings, but they're literally called strs, S-T-R. This is not a CS50 thing. The Python community calls strings STRs. But absent from this list is any mention of star, not to mention char star. There are no pointers in Python. And indeed, as powerful as I'd hope you found weeks 4 and 5 to be, I dare say you also found them incredibly frustrating and challenging and want to yield bugs in your code, because with that power of memory management comes a whole slew of potential mistakes that you can make. And that's true not just for CS50 students, but for programmers, adult programmers, full-time programmers around the world. And so among the other features of languages like Python is they try to take away certain features of languages like C that were just too dangerous in the first place. Might be wonderfully powerful, might help you solve problems more quickly, more precisely, but if they tend to do more damage than they're worth, sometimes it's worth just abstracting those details away. Similarly, Java has references, as some of you might know, but does not have pointers per se. You can't go poking around arbitrary locations in memory in the same way that you can with C. So let's take some of these data types out for a spin. And see what's the same and what's different. Let me go back to VS Code here, and let me propose that we bring back one of our old calculators from a while back. So let me clear my terminal, close hello.py, and let me go ahead and open up a version of this program that I brought in advance, which was our calculator version 0 from back then. So just to remind you, one of the first versions of our calculator had the CS50 library, as well as the standard I/O library. And then we simply got an int using getInt in week 1. We got another int in week 1 using getInt. And then we simply performed some additions. It was a very trivial calculator that we did very early on, just a demonstrator.py, which I'm just going to drag over to the right just so we can see both side by side. I won't bother with, say, well, let's do it for parity here. Let me copy the C code into the Python file, even though this will not work in the same way. But let's keep what we need and get rid of what we don't. So instead of the // for comments in Python, turns out the convention is to use a single hash symbol like this. So it's a minor difference. It's half as many keystrokes, so that's nice. But we're not going to include anything like this. But we are going to do from CS50, let's import a function that I promised would exist called getInt. But we'll soon get rid of that training wheel as well. We don't need main or this curly brace. We don't need this curly brace. And we don't need all this indentation as a result. So I'm going to move all of that over to the left. I'm going to fix all of the comments to be Python comments by changing the // to hash symbols. And now I'm going to change each of these 3 lines of code, as you might expect, to the Python version. So you probably can guess already, we can get rid of the int there and the int there. We can get rid of the semicolon here and the semicolon here. We can get rid of the f in printf here. And we can get rid of the semicolon here. And there's a few different ways we could do this, but I dare say the simplest is going to be to get rid of the format code altogether in that first argument and just tell Python to print x plus y. So there's a few different ways we can do this, but that's probably the most literal translation of the program at left to the program at right. Let's reopen the terminal window and run Python of calculator.py and hit enter. Let's do something like x is 1, y is 2, and hopefully we do, in fact, get 3. All right, so that's all fine and good, but let's take off one of our training wheels now. So let me get rid of our C version here and focus just for the moment on Python. Let's take away this C code. And what was the function we can use to get user input? It was called, a little louder? It's just called input. So let's get rid of CS50's getInt already and use input instead. All right, so this program's much simpler already. So let's go ahead and reopen the terminal window, run Python of calculator.py, do 1 again for x, 2 again for y, and of course, 1 plus 2 equals 12. So what's going on here? 1 plus 2 equals 12. And of calculator.py, do 1 again for x, 2 again for y, and of course, 1 plus 2 equals 12. So what's going on here? Because clearly this is a step backwards. Yeah. Yeah, so in the context of strings, plus represents concatenation, the joining of 2 arguments on the left and the right. Here, that seems to be what's happening, because it's not 12 per se. It's more literally 1, 2 concatenated together. But why is that? Well, apparently, the input function indeed returns a string. Those are the keystrokes that came back from the user. Might look like numbers and Arabic numerals to us, 1 and 2, but it's being treated as a string. More technically, like underneath the hood, there is some char star stuff going on there, even though we're not using that same terminology. So intuitively, what's going to be the solution without just reverting to using the training wheel that is the getInt function from CS50? Put another way, how did CS50 probably implement getInt, might you think? Yeah. Yeah, so recall that in C we could cast some data types to other data types, typically ints to chars or chars to ints. It's not quite as simple as casting in this case, because underneath the hood, thanks to our knowledge of C, there's a bunch of stuff going on. There's probably a 1, and there's a null character, there's a 2, and there's a null character. So it's not quite as literal as a char to an int or an int to a char. So we're going to more properly convert the string or the stir to an int. We're not casting, but converting. And converting just implies that there's a little more work that has to be done. But thankfully, Python can do this for us. In fact, let me go up to line 4 here and say, pass the, well, actually, let's do this a couple ways. Let's first convert the x value to an integer. Let's convert the y value to an integer as well. So funny enough, it's very similar syntactically to casting, but in C, when you cast something, you actually wrote the data type in parentheses. Now the data type itself is a function that takes an argument, which is the str or string that you want to convert. So let me go back to my terminal, do Python of calculator.py, enter, type in 1, type in 2, and now I get back my 3 answer. Now, as you might imagine, just like in C, we can kind of play around with where we're performing some of these operations, and this looks, arguably a little less obvious now as to what is being added. So I really like the simplicity of x plus y, just does what it says. So I could convert these in other ways. I could say after line 4, you know what, change x to be the int version of x. But generally speaking, that's kind of wasting a line of code by just doing something you could do on a single line. So let me delete that, and instead just say that, well, if I know the return value of the input function is a str, let's just pass that output as the input to the int function, and it'd be a little more Pythonic, so to speak, to just pass the input function's output as the input to int, which is really hard to say, but we've done this in C, just nesting function calls like this. All right, so if I run this one more time, Python of calculator.py, type in 1, type in 2, we're back now in business. Now, what I won't trip over just yet is a subtlety that whereby I'm deliberately typing in actual numbers like 1 and 2, but if you are following along at home or on your laptop, if you were to type in cat and dog, like bad things will happen, but we'll come back to that before long. All right, questions though on any of this conversion of our strings to our integers in this case? Oh, all right, well, what more does Python offer to us? Well, in addition to these data types, there's actually going to be a bunch of others, a few of which will actually of an array that's all of the Python, just so you know, there are a whole bunch of functions. These, though, were the C versions. In Python, it stands to reason that we don't need as many because there's fewer data types in Python, but get float, get int, and get string do all exist in the CS50 library for Python. You're welcome and encouraged to use it because, indeed, among the goals for problem set 6 are going to be to redo some of your C problem set problems already, but you can also just separate them by commas like this, or it turns out you can also import the whole CS50 library, as you'll see in some code, and then just access the functions within with slightly different syntax as well. All right, how about another construct from Scratch and from C, now, in fact, in Python? So in Scratch, if we wanted to do a comparison, like is x less than y, where each of those are variables, then say as much here. In C, it looked like this. And nicely enough, you can probably guess already what's going to change here. Like the f is about to go away, the \n is about to go away, the semicolon's about to go away, but some other stuff's about to go away as well. Focus your attention on the syntax like parentheses and curly braces, because in Python, it's just that. So we got rid of the parentheses because they didn't really add all that much logically. We got rid of the curly braces, which technically we could do in C anytime there's a single line of code inside of a conditional, but for consistency stylistically, we always use them as well. Python, though, does not have you use any of those curly braces at all, but Python requires that you indent your code properly. So if you've ever been among those who are writing out your program and like everything is just crazily like left aligned and just a big mess until style50 swoops in and cleans it up for you, you're not going to be able to write Python code like that anymore in syntax as well. All right, how about another construct from Scratch and from C, now, in fact, in Python? So in Scratch, if we wanted to do a comparison, like is x less than y, where each of those are variables, then say as much here. In C, it looked like this. And nicely enough, you can probably guess already what's going to change here. Like the f is about to go away, the \n is about to go away, the semicolon's about to go away, but some other stuff's about to go away as well. Focus your attention on the syntax like parentheses and curly braces, because in Python, it's just that. So we got rid of the parentheses because they didn't really add all that much logically. We got rid of the curly braces, which technically we could do in C anytime there's a single line of code inside of a conditional, but for consistency stylistically, we always use them as well. Python, though, does not have you use any of those curly braces at all, but Python requires that you indent your code properly. So if you've ever been among those who are writing out your program and like everything is just crazily like left aligned and just a big mess until style50 swoops in and cleans it up for you, you're not going to be able to write Python code like that anymore. That's been such a societal problem among programmers, newbies and professionals alike, that the language itself requires logically that if you want this line of code to execute, if this Boolean expression is true, you've got to indent this line by convention 4 spaces. You can't be lazy and leave it all left aligned and sort of fix it up later. This has made Python code arguably more readable because of these language-based requirements. Meanwhile, let's look at a if-else construct in Scratch, which looked a little something like this. In C, it looked like this, which is kind of a lot of lines just to express a simple idea. All of those same things are going to go away, whereby in Python, it looks like this instead. And the only other difference worth calling out is that because you don't have the curly braces, you do have a colon, which precedes the subsequent indentation as well. Meanwhile, if we've got an if else in Scratch, in C, of course, it looked like this. A lot of this is going to go away in the flash of a screen, but there's going to be a curiosity, which is not, in fact, a typo. Notice what happens with the else if. It's abbreviated elif. And honestly, to this day, all these years later, I can never remember if it's elif or else if because different languages use different shorthand spellings of this phrase. It's elif in Python because that's maybe the most succinct you can make the two words themselves. But everything else is effectively the same, including the additional colon this time. OK, questions on any of those conditionals and syntax? Yeah? A good question. What language did they code Python in? The interpreter we are using within VS Code is itself written in C, aka C Python. However, you can implement a Python interpreter really in any language, including machine code, like raw zeros and ones if you have that much free time. In assembly language, which we saw briefly weeks ago, you could write an interpreter for Python in Python if you really want to be meta about it, or in C++ or in Java. This is the thing about programming languages. You can use any language to create a compiler for or interpreter for another language. What's going to vary is just how easy or difficult it is and how much time it therefore takes you. Good question. Other questions on any of these here features? No? All right, well, let's do something a little bit a ver comments, which the variable if it's less than, greater than, or ... the converting Python version over to the do x equals get int and ask the user for what's x question mark. Then it's greater than y. Go ahead and print quote unquote x is greater than than y, else, colon, let's go ahead and print out, quote unquote, x is equal to y. So I dare say these are now equivalents. It's clearly fewer lines, because a lot of the lines at left were admittedly comments, but also some curly braces, and there's more syntax like parentheses that we got rid of too. Let me open my terminal window. Let me run Python of compare.py. We'll type in 1 and 2. 1 is less than, x is less than y. Let's do it again using 2 and 1. X is greater than y. Let's do it one last time, 1 and 1. And of course, those two now are equal to each other. All right, but why go down this road again? Because that was kind of a simple exercise. But recall that we introduced this comparison of ints because it was so sort of stupidly simple, even if the syntax that week was completely new. But we ran into an issue pretty fast when we started comparing strings. And that was a problem we really only fixed in week 4 when we finally revealed what a string actually is. If we focus a bit more on Python strings, it turns out that we can solve that problem much more easily in the world of Python. In fact, let me go back to VS Code here. Let me close these two versions of int comparison. Let me open up at left a version of my program that I brought with me here that contains a version from week 2, wherein we finally revealed that a string is just a char star. But recall that the solution in week 4, as well as in week 1 when we first encountered this problem, was to use strcomp, a function whose purpose in life is to compare two strings character by character by character using a for loop or something like that. But they have knowledge, therefore, of how to navigate pointers, how to look for the null character, the \0 at the end, and all of that came from our friend string.h. Well, how can we go about implementing the same idea in Python? Well, let's open up VS Code's terminal window, open up a new program called compare.py, but this time let's get rid of the integer version thereof. Let's get two ints from the user, and I won't even use any CS50 training wheels. Let's just use the input function to get s and ask the user for a value of s. So s colon close quotes with a space, t equals input, ask the user for a variable t, and then let's just ask the question, if s equals t, then print out quote unquote same, else go ahead and print out quote unquote different. Let me move these side by side just so you can see the difference. Notice how much code we have to write and how much we needed to understand in order to compare something as trivial as two strings in C. But in Python, been maybe cat for S and dog for T, and those are in fact different, but we would have gotten the same answer in C. Let's rerun Python of compare.py. compare.py and type in cat again, and now it's detecting them the same. So wonderfully, Python rerun Python of compare.py and type in cat again, and now it's detecting them the same. So wonderfully, Python has solved that seemingly annoying problem of not taking n or t, and those are in fact different. But we would have gotten the same answer in C. Let's rerun Python of compare.py and type in cat again, and now it's detecting them the same. So wonderfully, Python has solved that seemingly annoying problem of not taking us literally, like don't compare the pointer against the pointer. Compare what a reasonable programmer probably really cares about, the values of those strings. So the equal equals is doing all of the for loop or the while loop, iterating over those things character by character, and actually giving us the answer we want. So what else gets easier in Python? Well, let's focus a bit more on these strings. Let me go back into VS Code here. Let me close out our two comparison programs and clear my terminal. And let me go ahead and open up a prior program that we wrote, that one called agree.c. And namely in the staff version of the code online, this was agree2.c, which is where we left it. Out that the user agreed. Otherwise, if they type in anything else for that character, we simply print it out, not agreed. Well, how can we go about implementing that same program in a variable, say call before? No need to use the CS50 library because the input function here suffices. And instead of using C, I'm deliberately using S because it turns out in Python, there is no way to get a single character per se, but you can the user. Let's now go ahead, capital Y, or, and now notice English-like, a little more readable, top to bottom, left to right, and indeed, or hits that nail on the head. Otherwise, if it is not in capital Y or lowercase y, let's go ahead and print out, quote unquote, not agreed. It would be thing like this and just start oring together more possibilities like or, s equal, and so all of the possibilities, I can simply create a list of values from the get. Echo, or as we'll eventually see, I can add things to it, remove things from it, and all of the underlying memory gets managed for me. And in fact, with lists, we get a whole bunch of features that can make this possible. But for now, let's use them simply as statically initialized lists with values I know from the get-go that I want. And I'm going to go ahead and do this. In VS Code, I'm going to delete most of this Boolean expression, the combination of all of those there phrases, and I'm going to simply say if S is in, using a Python keyword in, literally the following list of values, quote unquote Y, comma, quote unquote yes. And for now, I'm going to use just those two, but let's see how it works. Let me open up my terminal window again. Let me run Python of agree.py, really for the first time, but let me claim that it would have worked even in the previous version. Enter. I'm going to go ahead and type in lowercase y, and I've agreed. I'm going to go ahead and run it again, and type in lowercase n, and I've not agreed. I'm going to go ahead and run it again, and I'm going to type in all caps, yes, because I really agree, and yet I don't, because there is a bug still in this version. So even though up here in my Python implementation, I do have a list of values that I'm looking for. Python's going to look literally for those values, so lowercase y and lowercase yes. So how can I go about tolerating different capitalizations by the user? Well, I can do this in a few different ways. I could, for instance, after getting the user's input in a variable called s, I could update s to be s.lower, which is going to have the effect of lowercasing the word for me and then updating the value itself of s. And now I think this will work even for an uppercase version. Let me go ahead and run python of agree.py, emphatically type in yes, enter, and yet this time I've agreed because I've forced the user's input to lowercase, and then I have compared against the canonical forms I've written, which are all lowercase. I could have done the opposite. I could have forced the user's input to uppercase and then enumerated in my Python list in between those square brackets capital Y and capital YES, but either approach here is fine. Now, technically, I don't need this additional line here. Here, I can go ahead and delete that line wherein I lowercased it, and in Python I can actually chain some of these function calls together by saying input.lower so that the return value of input ultimately gets forced to lowercase by using .lower here. Alternatively still, I could just lowercase at the very moment I'm actually comparing it, and down here I could do s.lower and then compare the lowercase version of what's going on to y or yes. Now what's really this all about? Well, this is actually an example of what's generally known as object-oriented programming, or OOP for short, whereby in Python and a lot of other languages, now you can have variables and data types more generally that have not only values associated with them, like y or yes, but also functionality built in. In other words, whereas in C, we would have used a function from like the C type library called toUpper or toLower, and we would pass as an argument to those functions the very character that we want to force to uppercase or to lowercase. Well, in Python, and indeed object-oriented programming languages in general, the developers behind the language recognize that sometimes there's functionality that's inherently related to the values in question. Indeed, when we're dealing with strings, it's pretty reasonable to want to sometimes uppercase them or lowercase them, capitalize them, or do any number of other things. And so built into the string type in Python is in fact the lower function itself, as well as a whole bunch of others. In fact, at this URL here, can you see the documentation for all of the string functions built into Python? And more technically, when a function is built into a data type and you access it via this dot notation, instead of by calling some global function and passing an argument into it, you are using what are called methods. So methods are simply functions that are inside of objects. And in this case, the object in question itself is a string. So what's really happening with this here example, when I'm checking whether the user is agreed or not, is I'm taking that value, that string s, which is technically now an object in memory, and inside of that object is not only the user's input, but some built-in functionality otherwise known now as methods. And those methods were written by the same people who invented the string data type itself. So this is just the first of these examples, but we'll see yet others. But notice the syntax is actually quite similar to C. Just as in C, when you wanted to go inside of a structure, you can similarly go inside of an object in Python and access not just the values ultimately, but also these built-in methods. All right, how about another comparison of C to Python, again involving strings? Well, let me go ahead and reopen and clear my terminal and close out of agree.py. Let me go ahead and open up a version of copying strings from a couple of weeks back, whereby we finally started solving it correctly by doing some proper memory management. So here in the staff version of copy5.c, we have not only a commented version of what we did a couple of weeks back, but we also have a reminder of what was involved in copying strings in C. Recall, for instance, that we prompted the user in this example, using CS50's getString function, for a string that they wanted to make a copy of, and then we did some error checking ultimately to make sure that there was enough memory and nothing went wrong. Then recall that the right solution to this problem in C was not to just use the assignment operator and assume that S can be copied into T, but rather to allocate, using malloc, enough memory for the copy, plus one more byte for the null character, again making sure that all is well by checking the return value of that, and then actually copying character by character by character the characters from S into the chunk of memory now known as T. Or ultimately, recall, we used a built-in stir copy function which does all of that looping for us. And then when it came time to capitalize just the copy, we did a quick sanity check. Is the length of T greater than 0? Otherwise there's nothing to capitalize. And if so, go ahead and use the C-type library's toUpper function, passing as input that with object. So it was a decent, let me go ahead and do this. And type in, say, cat in all lowercase and hit enter. And now notice, S remains in all lowercase, but the copy indeed has been capitalized alone. All right, let's take a look at one other example involving strings between C and Python equivalents. Let me go ahead and remind us that a few weeks back too, we created this uppercase program whose purpose in life was to prompt the user using getString for a string, saying here's the before string. Then it prints out after, because the purpose in life of this program was to uppercase all of the characters in the string, not just capitalize the first one. So as you might expect, we used a loop a few weeks back and we iterated from 0 on up to the length of the string using ++ to increment I in each iteration. And then each time we went ahead and printed out one character at a time. So strictly speaking, we didn't change the string from lowercase perhaps to uppercase. We just changed each letter to uppercase and printed it out right away. Well, how might we do something similar in Python? Well, here too, we have a couple of different approaches. Let me go ahead and open up my terminal now. Run code of, say, uppercase.py, close my terminal window, and let's drag this to the right so we can see them side by side. And let's do roughly the same. Let me create a variable, this time called before, set that equal to the return value of input, and just prompt the user for that before string. Then after that, let's go ahead and print out preemptively after colon, space, space, just to align everything nicely. But let me not print a new line yet because I want to go ahead and see the following string on that same line. And then let's go ahead and do this analogously to the C version first, but then tighten things up. Here's how we can iterate in Python over every character in a string. I don't need to bother with I and indexing into the string or anything like that. I can, using a Python Python for loop simply say, for each character C in that string called before, go ahead and print out the uppercase version of that character, but don't yet print out a new line. But at the very end of this loop, go ahead and print out nothing but a new line. Let me go ahead and open my terminal, run python of uppercase.py, enter, type in cat in all lowercase, cross my fingers, and after each and every one of the characters is uppercase. And what's nice about this, if nothing else, is that this for loop in Python there on line 3 is pretty elegant, whereby you implicitly get access to each character in the string because that's how Python knows how to iterate over a string object. But it turns out we don't have to do this quite as analogously in Python as we did in C. We don't have to do it character by character insofar as Python is object-oriented, and these strings are objects, and those objects have methods. Those methods will actually operate on the entire string at once, unlike the more pedantic work we had to do character by character in C. So in fact, let me go ahead and close the C version here. Clear my terminal and hide it, and let's go ahead and make this quite simpler. Let's get rid of the for loop altogether, and let's get rid of that print statement altogether, leaving only the before variable and getting the user's input. And now let's create an after variable, set it equal to before.upper, thereby uppercasing the entire string called before and setting the return value to the after variable. And then let's go ahead and print using our old friend fstring after colon space space, and then interpolate the value of that after version. So now we're down to just 3 lines at that. Let me go ahead and reopen my terminal, python of uppercase.py, enter, type in cat in all lowercase, and voila, now I have capitalized the cat all at once. All right, before we take a break for some fruit by the foot, let's go ahead and take a look at Python's implementation of loops further. So in Scratch, recall that we implemented a loop with something like this. If I wanted to meow 3 times on the screen, I would literally use a repeat block. In C, it was a little clunkier to mimic that same idea. Like we could implement a variable called I and set it equal to 0. Then we could ask a Boolean expression, is I less than 3? If so, print meow, and then increment I using our old ++ friend, which in Python is now gone. In Python, we can do this almost the same, except I don't think we need the data type. I don't think we need the semicolon. We don't need the parentheses. While still exists. We don't need the curly braces, and we can't use the ++. We don't need the F. I mean, we're mostly just trimming clutter from this here implementation. So this is the C version. This now is the Python version. A little tighter, a little easier to read. It's pretty much the minimal syntax available to get the job done. So how can we actually have a cat meow in this case? Well, let me go into VS Code, and I'll stop doing everything side by side and just stipulate that we've done most of these examples previously in C. And in my first cat, well, I could certainly do it the easy way. And let me go ahead and create cat.py. And like we always started in the past with, I could just do meow, and then our old friend copy paste. And this, of course, was bad for bunches of reasons, but it gets the job done. In Python, if I want to do this, well, I can just borrow that same inspiration, and I could say set I equal to 0, then do while I is less than 3, colon, then go ahead and print out meow, and then go ahead and do I equal, or rather I plus equals 1 is maybe the most succinct way to express that same idea. All right, just to confirm that this works, Python of cat.py, enter, meow, meow, meow. All right, so how else can we do this, and how can we do this more Pythonically? This is perfectly correct. Many people might implement it this way, but it's not quite as succinct as we could alternatively do in Python. Yeah? Yeah, so we could maybe use a for loop, and in fact, let's go there because we don't quite have the same types of for loops in Python as we did in C. While loops are essentially the same, but for loops are actually a little bit different and actually a little bit better. So let me go into my code here, delete all 4 of these lines, and literally just say for I in this list of values, 0, 1, and 2, colon, print meow. In other words, in for loops in Python, you don't have the parentheses, you don't have the 2 semicolons, you don't have the initialization and the Boolean expression and the update. You just say a little more English-like for each I in the following list, or for each value of I in the following list. And what Python will do for us is automatically, on the first iteration, set I equal to 0. On the second iteration, set I to 1. On the third iteration, set I to 2. And there's only 3 things in the list, so that's it. And so just as before with the Y and the yes example where I use square brackets, similar to arrays in C, I was using a Python list of strings in that case. Here, I'm using a Python list of integers, 0, 1, and 2. And they're integers in the sense that they have no quotes around them, so they're obviously not strings. And I'm printing out meow this many times. And indeed, if I do python of cat.py again, I get meow, meow, meow. This is correct. This is arguably better, at least in the sense that it's 2 lines of code instead of 4, and it's arguably more readable as well. But what do you not like about this, perhaps, even if you're only seeing it for the first time? Yeah, it's going to be a lot more difficult to do things more than 3 times because recall in Python and Scratch at least, and in C, we had the ability to either express ourselves literally, or at least in C, we could just change that 3 to any number we want, 30, 300, no big deal. It's a super simple change, even though it was kind of annoying to type all of this out. Well, in Python, yeah, I could do this and say for I in 0, 1, and 2, just to mimic the numbers that we'd be setting I equal to in the C version. Frankly, this can be any list. It could be 1, 2, 3, 4, 5, 6, cat, dog, bird, or any 3 things whatsoever, but I'm just using 0, 1, and 2 for consistency with the way C would have done it. But slightly better than this is to use one of those other data types that was briefly on the screen earlier on up. So just because you're doing more more iterations. So now if I do want to iterate 4 times, 5 times, 30 times, 300 times, I again can just change the single value. And if you want to be fancy too, you can skip numbers, you can go count all the way through odd numbers or even numbers, you can change the incrementation factor, but the default and the most canonical is indeed just to count up like that. So if I go back to VS Code here and improve this, I can change that hard-coded list to just range of 3, clear my terminal, run this cat one more time, and now I'm back in business as well. In fact, this is so common, let me throw up one alternative to this. You'll notice that in the previous example, both in VS Code and on the screen, I am not actually using I in any way. In fact, if you look back at how we converted the Scratch to Python code, I'm using I because when you use a I, you'll notice that in the previous example, both in VS Code and on the screen, I am not actually using I in any way. In fact, if you look back at how we converted the Scratch to Python code, I'm using I because when you use a for loop in Python, you have to give it a variable in some list or range of values. It's just the way it is. But I'm technically not using or printing I anywhere, and that's fine. And so it's arguably Pythonic too. If you have a variable out of necessity, but you're not actually going to use it for anything useful, just call it an underscore instead. And even though this is weird looking, an underscore is a valid symbol for a variable name in Python, so it is Pythonic to just use this, just to signal to yourself later and to colleagues that, yeah, I'm using a variable because I have to, but it's not one I'm actually going to use elsewhere. It's a minor subtlety and not strictly necessary, but perhaps commonly done. All right, how about a couple final versions of cats then? So recall that if we wanted to do something in Scratch forever, we had a forever block, which literally did that. Well, in C, we couldn't quite translate that literally, so the closest approximation was probably this, while true, whereby you have a Boolean expression that by definition is always true, so the loop is never going to stop, thereby infinite, if you want to print out meow, meow, meow on the screen ad nauseum. In Python, you can do it almost the same, but the curly braces are about to go, the F is about to go, the \n, the semicolon, and the parentheses, but for whatever reason, in C, we lowercase true and false. In Python, we capitalize true and false. So a minor subtlety, but it's now indeed capital T. But the indentation has to be the same, and the colon has to be there as well. So with that, we can, of course, induce intentionally or otherwise some infinite loops. As with C, you can break out of them if need be with Control-C to interrupt the process. But let's just see, lastly, with this cat, how we can make it a little more abstract like the final versions of our cat in Scratch and C. So let me propose to open up here in a pro version of cat that we looked at, that we wrote in the past. It was version 12 at the time, which looked a little something like that. Well, how can I use a trick that allows me to define my own function? And the keyword for this is literally def for define, the name of the function, and then parentheses if it takes no arguments. You don't need the void keyword even if it takes no inputs. So let's do a simpler version of the cat first that takes no arguments, and then we'll add back that argument. How does a cat meow? It literally just says meow on the screen. So already we seem to be an improvement. I've got like 4 lines of actual code here versus like 20 or so on the left-hand side. Let's go ahead and run python of cat.py, enter, and we see the first of our errors, which is remarkable because usually I would have messed up by now. So here we have in Python the equivalent of like a compiler error message. The program has not run. It's tried to run. It's tried to be interpreted, but it encountered some error. These are generally called tracebacks in the sense that you see a trace back in time of everything the program was trying to do just before it failed. So if you call it a function, which call the function, which call the function, you see all of those function calls on the screen. I just tried to call one function, so it's a relatively short error. This is clearly a problem, and here's the type of problem, name error. The name meow is not defined. So intuitively, even if you're seeing Python for the first time, why is meow not defined, even though it's literally defined right there? Yeah, as smart as Python is vis-a-vis C, still kind of naive in that meow doesn't exist until line 4. So if you try to use it on line 2, too soon. All right, so in C, we fix this problem by initially just kind of hacking things together by just, all right, well, let's just define it up here and then move that down there. And that's totally reasonable. And in fact, if I clear my terminal and rerun python of cat.py, we're back in business. But I'd argue you can only do that so many times, especially once you've got a bunch of functions. You don't want to relegate like the main part of your program, which really this loop is, to the very bottom of the screen, if only because like that's the first thing you care about. I want to see at the top of the screen. That's the whole point of putting main at the very top. So what was the solution in C? The solution in C was to put the prototype for the function at the top of the file. That, though, is not a thing in Python. You don't just copy that first line of code, put it at the top of the file, add a semicolon, and then it works. Instead, the Pythonic way to solve this problem, for better or for worse, is to actually put your code in a main function. Main in Python has no special significance in this sense. It's just convention to borrow the name that so many other languages use as the main function in those languages. But you just wrap your function in a function main so that you're defining main, then you're defining meow before you're actually using the meow function per se. But I have made a mistake. If I run python of cat.py now, cross my fingers for good measure, and now the program does nothing. Why is that? Yeah, why is that? Oh, sorry, go ahead. Yeah, curiously, I never called the main function. So whereas in C and in Java and C++ and a bunch of other languages, main is special. Like main is the function by definition that is automatically called. Python has no such special magic. It's not going to call main for you just because you created it. In fact, I didn't even call that main function main. It's just a convention. But the solution is exactly that. Well, if the problem is that main wasn't called, at the bottom of this file, what I can do is just literally call main, which we would never have done in C, but this is conventional to do in Python, so that after you've defined main up here and then define meow down here, now you can call main, which in turn will call meow. But at that point in the story, both of those functions exist. So if I go down here and run cat.py again, now I see my meow, meow, meow. Now let me add one final flourish, because this version of the code in C, recall, actually let me specify how many times I want to meow, whereas here I actually have my for loop in main at the right, and I'm calling meow that many times. Well, what if I want to get rid of this loop over here and de-indent meow here and pass in literally the number 3 here? Well, in Python, you can just say inside of the definition of a function that it takes an argument, like n, you don't have to specify the data type. Python's smart enough to figure it out. Then in your function, you can use that, as with for I in range of n, go ahead and print meow. So now the right-hand version of this program is pretty much equivalent to the left-hand version of this program, as always using fewer lines of code. Let me go ahead and run python of cat.py, meow, 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 we're good. And then let me make one final change, if only because most every documentation you see online or website tutorials on Python will actually have you not just literally call main at the bottom, but you'll do this crazy syntax that solves a problem that we won't trip over in this class, but typically it's Pythonic to actually call main after asking the question if name underscore underscore equals equals quote unquote underscore underscore main underscore underscore colon main. This is a stupid mouthful of code that even I had to think about when I was typing it out if I got all the underscores correct. But long story short, this convention of using a conditional before you call main allows you to write more modular code in Python so that some of your files don't actually do anything other than define functions that you can then import into other files you write. So in short, this is the right way to do it, even though in CS50 it is unlikely that we are to trip over this bug. Questions now on that last piece of how we define functions in Python? Yeah. Good question, good eye. Why do I have 2 lines between my functions in Python? As you will see via style 50, it is Pythonic, that is Python convention, to separate functions in your code by 2 lines, whereas there is no such convention in C. So I'm trying to be consistent with what the world does. Yeah. If you want to count backwards in a loop, can you do that? Absolutely. You could use the range function in a different way, start with a much larger value and count down. But you could alternatively do that with a while loop. I would say that, yeah, you can make that work, but you shouldn't. It's just people don't do that, unless it does actually solve the problem for you. Other questions on this? All right, well, when we looked at C, recall there was a bunch of things that ultimately we couldn't do well. We ran into issues of floating point precision and integer overflow and truncation and all of these world's problems. There's still going to be some of those, but first let's take a fruit by the foot break and we'll be back in 10. Help yourself to seconds today. All right, so we're back, and let's use our remaining time together to focus not only on some of the problems that Python can solve more readily than C, but also some of the problems that remain. So here was a program early on in our discussion of C that had this weird bug whereby when we implemented a relatively simple calculator to divide 2 numbers, x divided by y, we experienced what we called truncation at the time, whereby 1 divided by 3 was curiously 0, and something like 4 divided by 3 was curiously 1, and we were losing everything after the decimal point. And this was true even if we tried using floats, because with truncation, recall, everything after the decimal point with integer math is simply discarded. So if you do int divided by int, you're going to lose what is after the decimal point. So let's take a look in Python at whether this is still actually a problem. So let me go back into VS Code here. We'll close out the C version thereof, and let's go ahead and create our own program called calculator.py. And in this version, let's modify the original, which just did some addition, and instead have it do some division instead. I'll get rid of my outdated comments and perform now division instead of addition by doing x divided by y. Python of calculator.py, let's try 1 and let's try 3, and oh, our fractions are actually back. So it turns out in Python, even when you're manipulating integers, if you divide one by the other, and the result logically should actually be a floating point value, that's what, in fact, you're going to get back. And you don't have to jump through the same hoops that we did before to actually force things to floats and then do floating point arithmetic and so forth. In fact, if you want the old behavior, it's still actually there, and you can use 2 slashes in Python to use the old integer division as opposed to what we're seeing here. But a typical programmer, I dare say nowadays, would want it to behave in exactly the same way. So truncation seems to be less, therefore, of an issue for us. All right, well, what other problems did we encounter at the time? Well, recall we had issues of floating point imprecision, whereby even when we divided something simple like 1 divided by 3, and in grade school we learned that was like 0.333333 repeating infinitely many times, we started seeing weird numbers that were not 3 at the end of that value back in the day in C. Unfortunately, that's a problem that's still with us. In fact, if I use the same program here, let me go into VS Code, and instead of printing out just x divided by y, let's go ahead and do this temporarily. Let me give myself a variable called z and set it equal to x divided by y, only because it'll be a little easier to see the formatting trick I'm going to use. Let's go ahead and print out a format string that prints out z, and for the moment, let me just claim that this is going to do the exact same thing. It's just completely gratuitous that I'm using an f string now as opposed to just printing out z, but if I do 1 divided by 3, we're still seeing 0.333. But we're only seeing just over 10 or so digits here. What if we want to see like 50 digits and really start poking around at what's being represented? Well, the syntax is a little weird, but in Python, using an f string, you can do tricks similar to what we did with the %f with printf and C. And if after my variable's name in this set of curly braces, I do a colon and then a dot because I want to see numbers after the decimal point and say something arbitrary like show me 50 digits after the decimal point and treat this as a float, this is a crazy incantation, I do think, of a format string. Even I am sort of cheating off of the paper in front of me, but this is how you format strings if you want to see them with a little more precision, or so I think. If I rerun Python of calculator.py and do 1 divided by 3, darn it, we're still in the same mess that we were before. Now, why is this? Well, it's still the case that I'm running the code on the same kinds of computers that I did before. It's still the case that these computers only have a finite amount of memory, and so even though I'm manipulating clearly floating point values, Python is only allocating, say, 64 bits to those float variables. And so there's only so much precision that's possible. And so what we're seeing is essentially the closest representation to an infinite number of 3s that we can represent using binary using a floating point representation therein. So still a problem. But I do think in Python, you'll find that there's so many more libraries out there, third-party software that comes not just with the language itself, but from others, whereby you can use libraries for more precise scientific computing that essentially implement their own versions of floating point values so that you can use not 64, but 128 or more bits than that when it really matters to some level of precision. Thankfully, though, one problem is at least solved for us, namely integer overflow. So recall that this was another problem we ran into, whereby if you try counting higher than, say, 4 billion, or even higher than 2 billion, if you're representing negative numbers, which halves the total range that you have available to you in the positive range, we ran into the situation where it somehow wrapped around, became negative, and then even ended up being 0 as a result. Well, Python, wonderfully nowadays, just gives you more and more bits as needed if your integers are getting larger and larger. So this is a wonderful feature, and that we've at least addressed one fundamental limitation we ran into in C, and this time the language itself provides us a solution. Python 2 has some pretty handy features as well. One of them is what are called exceptions. And so an exception in Python is a way of handling error conditions without relying on return values alone. So recall that in C, if you ever wanted to signify that something went wrong, you have to return, like most recently, like null, N-U-L-L, which was a special sentinel value. Technically, it's just the 0 address. And by checking for that, you can make sure that you know if you're getting back a valid pointer or not. And in other functions, if something went wrong, you might similarly have to check the return value, maybe checking for 0 or -1 or 1 or something like that. But return values were the only way in C that functions could communicate back to the programmer that something went wrong. And this is problematic because if you imagine implementing a function that's supposed to return maybe an integer, whether positive, negative, or 0, it's kind of unfortunate sometimes if you have to steal one of those values and say, you can't use this value. It's fine in the world of pointers because the world decided years ago we're never going to use the actual address 0x0, the 0 address, but that's still technically costing us 1 or more bytes of space. But in general, it's a bit annoying if your function can't truly return all possible values. Think about a function like getString. If something went wrong in getString, what do you want to return? Well, we saw in the CS50 library, we do in fact return null once we introduce that. But in general, wouldn't it be nice if functions could somehow signal out of band, so to speak, that something went wrong? So by that I mean this. Let's go into a new program that's inspired by one of our programs today. And in VS Code, I'm going to go ahead and close my calculator, open my terminal window, and create a new program called integer.py. So an integer.py, let's just play around with some integers and see what we can break. So here, I'll define a variable called n and set it equal to the input function, which comes with Python, just asking the human for some input. Then I'm going to go ahead and ask a question. Is the user's input numeric? And it turns out, if you read the documentation for strings in Python, they come with not just an upper function, a lower function, aka methods, but also an is-numeric function or method that tells you whether or not the string itself happens to be numeric. That is, looks like a number. All right, so I think if I do that, I could then do something like this. If n is numeric, I'm going to go ahead and claim that, in fact, it is an integer. Else, if it's not numeric, I'm going to claim that it's not an integer. I have no idea what it is. Maybe it's cat, maybe it's dog, maybe it's a mix of numbers and letters, but it's definitely not an integer as defined by a sequence of decimal digits in this case. All right, so let's try this out. Python of integer.py, enter, we'll type in 1, that's an integer. We'll type in 2, that's an integer. We'll type in 0, that's an integer. Type in cat, not an integer. So that seems to, in fact, work. But what if I wanted to immediately convert this to an int, as we did in the past? And so let me modify this a little bit here and say instead this. N equals not just input, asking the user for an integer, or rather, let's just ask them more generally for input. But let's assume that we want to convert this input to an int. And actually, we can go ahead and say integer here. All right, well, here, I'm going to go ahead and just print out the claim that, yep, this is an integer, because if we get to line 2, well, clearly we've handled the user's input correctly. In other words, how can I get rid of constantly checking the return value, how can I get away from constantly checking the return values of functions and make sure it is what I expect? All right, well, let's go ahead and run Python of integer.py now. Enter, type in 1, tells me it's an integer. Type in 2, tells me it's an integer. 0 tells me it's an integer. Type in cat. Notice this time what goes wrong. Whereas last time we saw this kind of traceback error message, it was a name error because I was using the meow function name too early. Now I'm getting a value error, which is a different type of error that relates to invalid literal for int with base 10 cat. Now that's a mouthful, so unfortunately Python's error messages aren't all that much better than Clang's error messages, but clearly, the interpreter does not like the fact that I'm passing something to int related to base 10, but that's quote unquote cat. And really, the best you can do with this kind of error is realize like, okay, it's clearly the case that cat is not an integer, so it's having trouble converting cat to an integer. It makes no logical sense. All right, so what's the gist of the problem? Well, I'm just blindly converting the user's input to an integer, even if it's not input, even if it's not an integer. Well, all right, well, I could rewind to the previous version of my function, use the isNumeric function, and then conditionally convert it, but I'm trying to move away from constantly checking return values of error messages. And wouldn't it be nice if I could somehow catch this value error and just deal with it if it happens? And in fact, you can. With Python exceptions, which exist in other languages as well, Java among them, you have the ability to sort of listen for errors happening inside of functions without having to rely on return values alone. So let me go back to VS Code here, clear my terminal, just to simplify things a bit, and let me literally say to the interpreter, please try to execute the following 2 lines of code, except if something goes wrong, like a value error, in which case go ahead and print out something like not integer. So wouldn't it be nice if you could just wrap all of the code you've written in CS50 thus far with try and sort of ask the computer politely, like, please try to execute this code. But that really is the semantics behind it. Try to execute these lines of code, except if there's an error, then do this other thing instead. And therefore, you don't have to check any return values. You can just blindly pass the output of the input function as the input to the int function, knowing that if something goes wrong inside of there, Python is going to execute this code instead, except when something goes wrong. So let me go ahead and run Python of integer.py now. I'll type in 1, and that works because it's trying to execute line 2 and succeeding. It's trying to execute line 3 and succeeding, so lines 4 and 4 never actually kick in. But if I try again here with cat, line 2 is going to fail. Line 3 is never going going to get reached because Python is immediately going to jump to this exception handler, so to speak, thereby catching the error or the exception and printing not integer instead. So it's a little bit of a weird convention. It's different from what C offers, but a lot of newer languages nowadays do offer this because it's a better way of just writing code that you know should work 99% of the time, but if something does go wrong out of memory, the human types something wrong in or something like that, you can handle all of those exceptional cases, exceptional in a bad sense, using this except keyword instead. Questions on any of this here technique? Yeah? A really good question. In this case, I used a value error. Do I need to define every possible thing that can go wrong? Short answer, yes. Now, there aren't terribly many. There's some standard ones, and they're all capitalized in this way, capital letter, something error, typically. You can even invent your own. And it's good practice to enumerate the kinds of things that you think can go wrong. Value error is pretty generic, but there could be memory-related errors. There could be file not found related errors. There's a bunch of different exceptions that are all documented in Python that you can listen for. That said, as nice as Python's documentation is overall, it is not good at documenting for specific functions what exceptions they can throw, and I've never understood this after all of these years that no human has gone into the documentation and painstakingly enumerated all of the possible things that can go wrong. What's too often the case in the real world, with some of my own code included, is if you encounter an exception that you didn't think was going to happen, you go in and improve your code and add to this list of except clauses what else might go wrong. Shouldn't be that way, and different libraries are better about documenting these things. All right, well, with that in mind, let me propose that in the CS50 library for Python, getInt and getFloat, they work just like the C library, whereby if you type in cat or dog or bird into those functions, they just reprompt you. And long story short, this is the kind of code we wrote in Python. Try to get input from the user, except if something goes wrong, prompt them again. So we too are using precisely these features, even though it wasn't something that was available to us in C. All right, but something else that we did in C was play around with Mario in a few different forms. And in lecture recall a few weeks back, we experimented with using some ASCII art, some very simple text to print out something like this pyramid of height 3. Well, how can we go about printing something like this? Well, I would propose that if I go back to VS Code here, let's close out my integer examples, code up a new version of Mario in mario.py. This one's kind of simple. I can say something like for I in range of 3, go ahead and print out, quote unquote, a hash. Down in my terminal window, Python of mario.3, and I've got really the closest analog to 3 bricks stacked on top of each other in hash. Down in my terminal window, Python of mario.3, and I've got really the closest analog to 3 bricks stacked on top of each other in this way. But in C, and eventually our implementation of Mario started to get a little fancy, and we started to prompt the user for the height of the wall, and therefore we could have not just 3, but maybe 4 or even more bricks being printed. So let me actually open up that version from a few weeks back, whereby from week 1 we had a version of Mario that looked like version of the wall, and therefore we could have not just 3, but maybe 4 or even more bricks being printed. So let me actually open up that version from a few weeks back, whereby from week 1 we had a version of Mario that looked like this, whereby we, after including some header, had a version of Mario that looked like this, whereby we, after including some header files, declared in main a variable called n. Then we saw a new construct at the time, a do-while loop, that just keeps using getInt, so long as n is not 1 or greater. Equivalently, so long as n is less than 1, and kept prompting the user again and again. The reason for having n up here, recall, was issues of scope. Therefore, it's accessible lower in the function as opposed to it being confined to those curly braces. And then down here, we used a for loop to actually print out that many hashes. So in short, the do-while loop solved the problem in C, whereby you want to get user input at least once, and maybe again and again and again if they don't cooperate the first time. And that's where do-while loops really shine. Do something at least once, and maybe again and again. Otherwise, it's a little more annoying to do it with while loops or for loops. Unfortunately, Python does not offer a do-while loop. And so here, too, we have an opportunity to introduce you to what the world would call Pythonic. What is Python's solution there, too? Well, on the right-hand side here in mario.py, let's change this a little bit, and let's do from, let's go ahead and do while true, capital T, go ahead and use a variable n, set it equal to int input height, asking the human for the height of the wall, and I'm going to just cross my fingers that I'm not going to type in cat or dog or something that's not an int in this case. I'm going to say if n is greater than 0, that is a positive number, that's useful, we can proceed. I'm going to now break out of this loop. And then lower in the file, I'm going to say for I in range of n, go ahead and print out the hashes. So we still have that same lesson as before, like the Python version seems to be shorter, more concise, even if you ignore the comments on the left-hand side. And I've completely avoided using a do-while loop, but there are a few things that are different nonetheless that feel like versus C shouldn't even work. Like, what's weird about this solution, even though I think it's actually correct? Yeah? I have two. OK, so it's not correct. That's one of the first things to point out. So too many prepositions for, this was supposed to say for I in range. OK, so now that this program's correct, what looks weird to you and probably could break it? Yeah. Yeah, so the end variable should be, it seems to be scoped to the while loop, at least insofar as it's indented inside the while loop, which feels analogous to being inside of curly braces in C. And so it seems weird that I'm presuming to use n on line 6, even though it was only defined on line 2. It turns out this is possible in Python. The issue of scope that we encountered in C is not as rigorously enforced, we'll say for today, such that when you define n up here, you can actually use it down here. And you can think of this as being a little reasonable because if there's no more specification of what data type n is and no more semicolon, just imagine it would look kind of stupid if you just put a blank n there and hit enter just so it kind of exists. There's no way to express the idea of create this variable in advance without actually assigning it a value, whereas in C we could do that. So this is in fact OK and correct. What else is going on here? Well, instead of a do while, we're kind of just implementing the idea of it. I'm just blindly inducing deliberately an infinite loop, like do the following forever, but then as soon as I have the answer I want, like a positive integer from the human, break out of this loop. And this is indeed the Pythonic way to say get user input, because this will minimally ask the user for height once and maybe more and more times. So no do while loops, only while loops, and for loops, and only while loops are really the same as in C. Even for loops we've seen are a bit different. All right, well, how about instead of just that Mario example, recall this one, where we wanted to print like 4 question marks in the sky, side by side. Well, we can do this in a few different ways. Let me go back to VS Code, close the C version, and let's just completely change Mario.py to implement this now. I want 4 question marks in the sky, so I think I can do something like for I in range of 4, go ahead and just print out quote unquote question mark. Do you like this? Python of Mario.py. Should I run it? No, bye. This is how I did it in C, yeah. Yeah, I got to edit the end value, the named parameter for the print function, because otherwise if I hit enter, they're all on different lines, which is not the effect I want when all 4 question marks are meant to be side by side. All right, well, that's an easy fix. I can pass the named parameter called end into the print function, set it equal to quote unquote with double quotes or with single quotes. As always, stylistically, I would be consistent, so I'm going to use double quotes even though the documentation is consistent with its single quotes. Now I'm going to rerun Mario of Python, Mario.py, and I'm so close. Now they're on the same line, but the stupid cursor didn't move to the next line. That's fine. How to fix this? Well, just logically, I can put a blank print statement below, and even though I'm not passing anything in, you get a new line for free when calling print. So even though I'm not passing in any arguments, I am getting the aesthetic effect that I want. So that is a perfectly reasonable way to do it. Now, if you feel yourself becoming a bit of a geek, though, in learning about Python, and it's previously a perfectly reasonable way to do it. Now, if you feel yourself becoming a bit of a geek, though, in learning about Python, and it's previously C, you can even solve this problem even more Pythonically by saying print, quote unquote, question mark, times 4, using multiplication simple print statement below. And even though I'm not passing anything in, you get a new line for free when calling print. So even though I'm not passing in any arguments, I am getting the aesthetic effect that I want. So that is a perfectly reasonable way to do it. Now, if you feel yourself becoming a bit of a geek, though, in learning about Python and previously C, you can even solve this problem even more Pythonically by saying print, quote unquote, question mark, times 4, using multiplication similar in spirit to the plus operator for concatenation, and now multiply the exclamation point by itself 4 times. So now if I go down here and run Python of Mario.py, I get a very elegant solution to exactly that same problem, even more concisely than my previous version. What if I want to do something in 2 dimensions? Well, recall that we moved to the underground of Mario Brothers here, and we had like a 3x3 grid of bricks. How can we do that? Well, in C, we had nested for loops using I and j back in the day. And I can do the same thing in Python. Let me go back into VS Code here, and let me do one outer loop for I in range of 3. Then let me do an inner loop for j in range of 3. Then let me go ahead and print out a hash. But let me learn from my past mistakes. I don't want to print out a new line every time, so let's override that default. But after each row, let's print a new line, so that down here, I can go in Mario.py, run it, and I've got my 3x3 grid of bricks. I can change this a little bit and call this row and column, even though here too, even more so, I'm not literally using row and column anywhere explicitly, but semantically, it kind of explains maybe a little clearer to the reader what's actually going on. So that might help. But we can tighten this up too, right? If I just want to print a 3x3 grid, well, I know that the top thing here will iterate 3 times, and I know how to very elegantly print things out with a one-liner, so I could just print out a hash times 3 in this case, and then down here I can go to Python of Mario.py, and voila, I'm back in business too. So it's just sort of easier to do these kinds of things and express yourself all the more succinctly. Well, what else can we do? Well, it turns out in Python that unlike arrays, you can ask lists how long they are. So you don't have to keep around a variable of how large an array is. You can just add stuff to a list and then ask Python, how long is this list? How many elements are in it? Case in point, let me go back to VS Code and clear out Mario.py, and let's re-implement from a few weeks back the notion of calculating like in the average quiz score that you might have in a class. So in score.py, let's go ahead and create a program that's got a list called scores of 3 scores that we've seen before, 72, 73, and 33. And recall that we tried a few weeks back in C to average these together. And to do that, we had to add them all together. We had to divide by the total number of elements in the list. It wasn't that hard. It was sort of like grade school arithmetic to calculate an average. But Python has more functions available to us, not just length, but even summation. So let me go ahead and do this. Let me say that my average variable shall be the sum of those scores divided by the length of those scores. And indeed, per the documentation, Python has a len function, len for short, a sum function, which takes which adds together all of the elements in that list. And so down here now, I can say something like print with an f string or format string that the average is whatever that value is. And I don't have to do any loops or math myself. I can just call the function like I could in Excel or Google Sheets or Apple Numbers. Python of score.py, enter, and my average is in fact 59.3333, and then some weird imprecision at the end there. And in fact, just for consistency with our C code, let me rename this. I'm going to rename score to scores plural. That's going to close the window, but now at least you'll see online that we have a program indeed called scores. Well, this is not that interesting because I've just hard-coded my 72, my 73, and 33. What if we want the human to be able to type that in? Well, I think we can do that too. So let me actually open up that version of the file, now pluralized. Let me go ahead and not initialize the list for the human, but let me set it equal to an empty list, just using an open square bracket and close square bracket, like an array that has nothing in it, but this one is literally of size 0 at the moment. And now let me do for I in range of, let's just for now ask the user for 3 scores, even though we could certainly ask the score using something like int input in my accept variable, the user's quiz score. How do I put it into that array? Well, in that list, well, because with it, I can just call a method that comes with every Python list called append and pass in that score using that same dot notation as before. The rest of my code can stay exactly the same. If I now run python of scores.py and I type in 72, 73, 33, manually though, I still get that same average. And notice I did not need to decide in advance how big that list of scores was going to be. Questions on what we've just done with lists? No? All right, even cooler, for some definition of cool, is that we can now implement hash tables, or more generically, dictionaries, sets of key value pairs, by just using a data type that comes with just a version of our just by putting 4 quoted in this list. And now let's implement linear search using Python. I can do this in a bunch of ways, but one way is to say for each name, we'll call it n in names, go ahead and ask the question. If the name I'm looking for equals the current name in the list that I'm iterating over, go ahead and print out just something generic like found, and then break out of this loop. And let's see if we can find Kelly or David or John or someone else. Python of phonebook.py, enter. Searching for the name, say David, enter. And it was, in fact, found. Let me go ahead and search for someone else's name that's not in there, Brian. And now it's not, in fact, found. Although it's not all that enlightening to just ignore the question altogether. It would be nice to say not found. And here is where in C, it would be kind of non-obvious to do this. In C, if you wanted to print out found, or if you get through the whole list and you still haven't found the user, print not found, you'd have to like keep track with a variable of whether or not you found the person, or you'd have to return from the code prematurely just to get out of it logically. Turns out, somewhat weirdly, but wonderfully usefully, for loops in Python can have else clauses associated with them, whereby I can say down here, print not found. If I run this version of the program and search for someone who's not in the phone book like Brian, now I actually see not found. Semantically, it's a little weird, but essentially what's happening is if you get through this whole loop and you never call break, then you've not actually broken out of the loop, so you're going to hit the else, and in that case, you're going to print out not found. And this is such a common thing to like do this kind of bookkeeping and keep track of whether or not something has happened inside of a for loop, and if so, do this, else do that. Else literally handles that scenario in Python, and this is the most C-unlike thing that we've perhaps seen in terms of features with regard to at least loops. All right, well, this is great that I've kind of implemented linear search, but like we did that in C and it's getting a little tedious. Can't we do better? We actually can. Let me clear my terminal and tighten this up. Instead of iterating over every name in names, just like we keep iterating over integers in ranges and checking for each name if it equals the thing we're looking at, you can actually do something much more clever. You can just literally ask Python if the name you're looking for is in the names list, then go ahead and print out found, else print not found. And so this is where Python 2 gets kind of cool. Go ahead and print out found, else print not found. And so this is where Python 2 gets kind of cool. In line 5, you have just a simple if condition with a Boolean expression, name in names. How does Python know if name is in names? It uses linear search, presumably, to search over the whole list of names, looking for what you care about, and then tells you true or false if it found it. You don't have to write the code to iterate over it with a while loop or for loop or whatnot. You just say what you mean. And so here, too, it's a little more English-like. If name in names, question mark, then print found. Much more so than it would be pronounceable in C. So that's where in Python, dictionary ourselves, store a dict object. How do we go ahead and hit enter just to move quote unquote key 750, which is fun to call or text. This now, even though it's syntactically a little different, gives me the equivalent of this chart here. Key value pairs, hash table exactly the same way. I'm going to go ahead and generalize this now to people because it contains not just names, but names and numbers. So I'm going to change this variable down here to people too. But notice the syntax now. I can still ask the human for a name they want to look up. I can now still say if the name is in the people dictionary, and by definition, Python's going to interpret that preposition in as meaning is the following key in the dictionary, and if so, it's going to return true. But what's cool about this is that besides just making this work as follows, Python of phonebook.py, and let's type in David, and there's my number. Oh, that's not my number, it just says found. Let's run it again and type in, say, Brian, not found. Okay, that's as expected, but I'd like to know what my number is, or Kelly's number, or John's number. Well, that's an easy fix too. Inside of this conditional, I can say something like this, number equals people bracket name. And we've not seen this before, but we have seen square brackets. In C, when we had arrays, this square bracket notation is how you index into an array to get a specific value. 0, 1, 2, 3, 4. What's amazing about dictionaries, not just in Python, but in other languages as well, you can now index into a dictionary, just as you can index into an array, but whereas in an array you use numeric indices, in dictionaries you use string indices. You can use strings to look up their corresponding value. So to be clear, name at this point is given to us by the human's input. So if I type in DAVID, name equals David. So this is like saying people, square bracket, quote unquote David, find David's number. That stores the answer from this 2-column chart in the variable called number, and all that remains is for me to print it out, which I can do using an old f string now. Let me go down into my print statement, change this to an f string, add a colon, add the number variable to be interpolated, rerun this program as Python at phonebook.py, type in my name, and there's my number as found. And this is incredibly powerful, and why, again, hash tables and in turn more generally dictionaries are sort of the Swiss Army knife. Being able just to look up data with such simple syntax is wonderfully useful and powerful. And in fact, we can even do more than this, for instance. Let me propose that if you think about other incarnations of key value pairs, you see them all the time, for instance, in like spreadsheets. Like here's a screenshot of Google Sheets whereby I've got the beginnings of a spreadsheet with names and numbers. But in this model, I want to actually associate some metadata with my data. So the data I care about is the actual names and numbers. But you can imagine having a third column like email address and maybe home address or any number of other pieces of data associated with these 3 people. For now, I've just got 2 columns or 2 attributes, names and numbers. Each of the rows in a spreadsheet, as most anyone knows who's used a spreadsheet before, represents different records or different pieces of data, like this is Kelly, this is David, this is John, and so forth. We can implement this idea using dictionaries and lists together. So the syntax is going to be a little strange at first, but let me go back to VS Code here, and let me change my people dictionary to be a people list between square brackets, and the elements of this list now are going to be dictionaries themselves. I'm going to use some curly braces inside of these square brackets and say that the name of one person is quote unquote Kelly, and the number for that person is quote unquote +1 617 495 1000. Close quote, then comma on the outside of the curly braces, then I'm going to have another quote unquote name, colon, DAVID, comma, then another number, colon, I'm going to borrow the same phone number because we both work here, then lastly, a comma, and finally, quote unquote name, colon, quote unquote John, and then lastly, a quote unquote number for John, colon, +1 949 468 2750. Whew. All right, so what's going on here now? Our people variable is now not just a simple dictionary with just individual key value pairs, name, number, name, number, name, number. We now have a more generalized way of storing not just a name or a number, but an email address or a home address or any number of other values. How? Well, the commas just separate the key value pairs now. So if I do have email addresses for us, I can put comma, quote unquote, email, colon, like mailin@harvard.edu, and I can just keep adding these key value pairs to each of the dictionaries, because a dictionary is a collection of key value pairs. So it stands to reason that I can associate name with David, number with the number, email with mailin@harvard.edu, and so forth, effectively implementing this idea now in the computer's memory. And at the risk of significantly oversimplifying, this is what Google and Microsoft and Apple are doing with their spreadsheet software. They have written code that presents to you a nice table with a graphical user interface on the screen, but underneath the hood, what they effectively have is lists of dictionaries representing each of those rows. And we're going to come back to this when we start experimenting before long with our own databases, getting back rows of data from databases. We are going to store that data in lists around the current person's name to that index, passing a comma into with those curly braces and form of libraries that come with the language. All right, a couple final features of Python that'll get us on our way with doing other things. Turns out there's a whole bunch of libraries that come with the language itself that you nonetheless have to import. Even though they're not third party, you didn't have to install them, you just need to add them to your code by importing them. One of them is sys. And among the things that the sys library has in Python is the ability to give you access to command line arguments. After all, we've lost access to command line arguments because there's no more main, at least by convention. There's no int main void, there's no int main, argv, argc stuff going on in our code. But all of that functionality is still available in a library called sys. So how do we use this? Well, let me go back to VS Code here now. Let me create a relatively simple program called greet.py, similar to a few weeks back, that's just going to greet the user using command line arguments instead of getString or the input function. I'm going to do this by saying from the sys library, import argv. In this case, argv is essentially just a list. It is a list of the command line arguments that the human has typed. It's a list, which means you can just ask the length function, len, what its length is. So there's no need for argc anymore. You can just literally ask argv how long it is, which is kind of nice. So I'm going to say this. If the length of argv equals 2, which means the human typed 2 words at the prompt. Okay, let's go ahead and greet them, assuming that's their name, and say hello, comma, and then whatever their name is. Let me make this a format string, and to be pedantic, let me create a variable called name and set it equal to argv bracket 1, which is going to be the second word that the human typed in, as has been our convention in the past. Else, if they didn't type exactly 2 command line arguments, let's just go ahead and print out something like hello world as generic. Let me run python of greet.py, enter, and you see hello world, because I apparently did not type in exactly 2 words, and yet I did. So let's see where this is going. Let me rerun python of greet.py, but type in my name David at the command line, enter. And, I screwed up unintentionally. What did I do wrong? All right, printf is not a thing. So that's an easy fix. Let's delete it. Let me clear my terminal window, rerun python of greet.py space David, enter, and now I get hello David. The only thing that's weird here is that I typed in 3 words at the prompt, and yet I'm checking for 2. And it's a bit subtle, but with Python and argv, it ignores the Python interpreter. It goes without saying that you're using the Python interpreter to run a Python program, so the only things that are being counted are the words after the Python interpreter itself. So when I type greet.py and David, that's 2. When I only type greet.py, that's 1 instead. All right, so now that I've done that, I have access to my command line arguments again. What about my exit statuses? This was getting a little low level, but in recent C programs, we've had you all returning 0 on success, returning 1 on error. Can we still do that? Well, yes, and in fact, the sys library is used for that as well. So if I want to actually add some exit statuses to a program to facilitate check 50 and automated tests in the real world, I can do that with a program called, let's call this exit.py. And in exit.py, I'm similarly going to import sys, but in a different way. I'm going to give myself access to, well, yes, let's go ahead and import the whole library just to demonstrate how you can access things inside of it without explicitly saying from sys import such and such. As before, if the length of sys.argv, so this is a little bit different, but I'm asking the same kind of question, does not equal 2. I want to go ahead and print out to the user missing command line argument, which is something we did a while back as well. And then I want to exit with code 1, sys.exit 1. Else, if I don't run into that issue, I'm going to go ahead. Actually, let's not even bother with an else. Let's, for parity with our C version, let's do this. Print f quote unquote hello sys.argv bracket 1 close quote sys.exit 0. All right, that's a whole mouthful, but what's really going on? So I could have done from sys import argv, but I don't need to enumerate every single variable or every single function that I want from a library. I can also just more generally say import the whole library, give me access to everything, and then I'll tell you what I want from it later. Therefore, on line 3, I can still access argv. I just have to scope it to the sys library so that I say sys.argv means go inside of that library and find me argv, instead of elevating it to a variable unto itself in my own code. Why am I saying not equal to 2? Well, if they don't give me 2 words after the interpreter's name, I want to yell at them and say missing command line argument and then exit 1. I'm not going to give them a default hello world anymore. I want them to give me their name. Meanwhile, if I get this far and I haven't exited from the program, I can print out sys.argv bracket 1, which is going to be David in the example I typed before, and this means success, so sys.exit 0 signifies success. It's more syntax than before, than it was in C, but we have the exact same functionality available to us as we have in the past. How about one other example that we've had in the past? Let's convert it to Python as well, so you have a few more tools in your toolkit. How about implementing a version of this phone book that actually persists? So instead of hard coding into it, Kelly and David and John in this way, let's actually let the user type in a name and a number, just like on your iPhone or Android phone, and add it to a text file, like a CSV file, as we did before, using comma-separated values. Well, it turns out that Python comes with a library to handle CSV files. We don't need to hackishly implement our own CSV support by printing the comma as ourselves. Instead, we can import the CSV library. We can then create, say, a variable called file, set it equal to open, and open a file called phonebook.csv in append mode. So this is almost the same as C, except it's open instead of fopen, which we saw a couple of weeks back. Now let's ask the user via the input function for the name they want to add to their contacts and the number that they want to add to their contacts. And then after that, let's go ahead and do this, which is a bit of muscle memory to remember. But I'm going to create a variable called writer. I can call it anything I want. Set it equal to csv.writer, which means there's a function called writer in the CSV library that I'm simply accessing it because I didn't import it explicitly by name. And I'm going to pass it that file. This tells Python, turn that file into a CSV that can be written to. The next line of code, I'm going to literally say writer.writeRow. WriteRow is a method, aka function, associated with this writer object. And I know that only because I did actually read the documentation for the CSV library. What do I want to write? Well, I want to write a list of values, namely a name and a number. And I'm using square brackets to tell the writeRow function that here you go, here's a list of values, 2 of them, a name and a number. After all that, I'm going to do file.close and just close the whole file. All right, so where does this actually get me? Well, let me go ahead and open up phonebook.csv, which is initially empty. I'll move this over to the right-hand side. But when I now run this program with Python of phonebook.py, enter, I'll type in, say, Kelly's name, enter, +1 617 495 1000, enter, and voila, it ends up in the CSV using a little bit less code than we had to last time with C. Let's run it once more, and I'll type in my name, and I'll again use +1 617 495 1000, enter. It's being appended to that file as well, and one last time for John, +1 949 468 2750, enter, voila. So it's pretty easy, that is to say, in Python to start creating files like this. 9468 2750, enter, voila. So it's pretty easy, that is to say, in Python to start creating files like this. But this isn't really Pythonic. Let me, in fact, close the CSV file, hide my terminal, and propose that we can tighten up this code a bit too. I don't need to open up the file way up here. I can go ahead and get my variables values this way first. In fact, I could have done that code a little later anyway, but I can do this in Python. I can say, with the following file opened, phonebook.csv in append mode, and refer to it as a variable called file, do this stuff, and close the file yourself. So this program's suddenly significantly shorter because this one line has the effect of opening the file for me in append mode, assign it to a variable, do this. This just helps me run putting some code inside of phonebook.py that writes out that specific row, because after all, if I'm going to ensure that I notice that I don't have to rely on this typed in. And let me go back actually now and fix a typo from earlier. We're only asking the user for one number, so all this time I should have just requested one number aesthetically with my input function there. Now notice I have the file ready to go. Indeed, name and number are there. That matches the field names I've provided to my code, and it otherwise empty, say 2750, which if you still haven't called or texted, do feel free. Enter. And voila, in phonebook.csv, we have all of those same rows and code that's a little more resilient now against any changes we might subsequently make. Name what you need, including space line in the repository. Install this line of cow.py, enter, mod for you. Cross my fingers, and there's the most adorable cow, and if we full screen the terminal, we'll see that he's indeed saying this is CS50. Now that's just one of the